Okay, so dynamic games models are very useful because that allows us to discuss a lot of different situations in practice or in the business world. Here, let's discuss one application. It's about pricing in a supply chain. I'm first going to give you the model and then give you the insights we may obtain from this simple model. Eventually, you will feel this model is so simple. Okay, and actually, this model has been proposed about 60 years ago. It somehow rigorously or mathematically shows something that we believe, which is intuitively true. Okay, I'm going to start. So suppose there is a supply chain. That means there is a manufacturer and a retailer. The manufacturer produces the product, shipped to the retailer, and then the retailer sells the product to the consumer. A supply chain somehow just means a process or several entities that together produce, ship, and deliver the product to consumers. Okay, so graphically, there is a manufacturer sells to a retailer, retailer sells to consumers. The manufacturer makes the product, and the retailer sells the product. So the manufacturer will set the wholesale price, W. Okay, wholesale price means the unit price selling to the retailer. Okay, the retailer buys at the wholesale price and then sell at the retail price to consumers. So naturally, R should be somehow greater than W because R minus W is the sales margin for the retailer. In this problem, we say the market demand, is affected by the retail price R. And we again use this very basic linear demand model. So demand is A minus BR, and A and B are known constants. When the retail price becomes larger, the total demand will become smaller. We may also say that there is a unit production cost C, and that's how manufacturer pays to get those products. Always we want to ask, in this game, what is the equilibrium? Okay, what will the two players do in equilibrium? What will be the equilibrium wholesale price? What will be the equilibrium retail price? And how much they may earn, how much the consumers may earn, and so on and so on. We want to know what's going to happen in this situation. Okay, to make the derivations easier, let's say A and B are just 1 and C is 0. Okay, we're going to show you our derivations under this assumption, but I hope that you may take away this assumption and do the remaining analysis by yourself. You're going to see that nothing really changed. All the insights, all the ideas we may get at the end does not change when you assume A, B, and C are general values. Okay, so let's solve this game with backward induction. The first thing is that we need to worry about the retailer. The retailer thinks that W is given. Okay, for the retailer's perspective, W is nothing but a constant. So the retailer is facing a trade-off. If I set my price to be lower, then for each unit I can earn a less money. Okay, but if I set my price to be high, then fewer consumers are going to buy from me. So I'm making a trade-off between profit margin and the sales volume. So that's how naturally this becomes a nonlinear problem with a concave objective function. So the retailer's problem is here. I want to maximize something. What's that? My total profit. R minus W is my unit sales margin, and 1 minus R is my total demand according to my retail price. Here, W is a constant. W is a parameter given by the manufacturer. If we think about this problem, this is exactly a convex program, right? Because the objective function is concave. Okay, the objective function is concave, and then with first order condition, we can solve this problem immediately. The optimal solution or the best response for the retailer is the following. Given your wholesale price W, I'm going to set my retail price to be W plus 1 over 2. Okay? If W is 0, I'm going to charge 1 over 2. If W is 1, I'm going to charge 1, and so on and so on. Of course, you may want to ask whether W may be greater than 1. We're going to show you that's impossible. Okay? And if W is within 0 and 1, then you don't need to worry about whether the demand will become negative, because W will also be within 0 and 1. Okay? So anyway, you know one thing. The equilibrium retail price is a function of the wholesale price. When your wholesale price becomes larger, of course you will be forced to make your retail price higher. Okay? Because you need to retain a reasonable sales margin to maximize your profit. Your retail price will be increased by a higher wholesale price. Okay, so then we may move back to the manufacturer's part. The manufacturer now knows how the retailer will do. So given W, the retail price must be this. So as a manufacturer, I can calculate the equilibrium order quantity. I don't really care about how much money the retailer earns, but I care about how many units the retailer buys from me. So 1 minus R star is the equilibrium demand, and that's the order quantity ordered by the retailer. So I can plug in W and I'm going to see that when I increase my wholesale price, the demand is going to become smaller, okay, naturally, because even though the customers does not see the wholesale price, when my wholesale price becomes larger, the retail price will also becomes larger, and that's going to hurt the total demand. So now the manufacturer can formulate her problem. Sales margin is W because there is no cost here, and the demand as a function of W is here. So we can see again, this is a concave function. This is a convex program. First order condition, we can see that optimal wholesale price is 1/2. Okay? The manufacturer as the leader will choose 1/2 as the wholesale price. That does not depend on the retailer, of course, because player 1 is, manufacturer is the leader. Okay? The retailer's optimal strategy is contingent on manufacturer's wholesale price. Okay, like this. This is retailer's optimal strategy. But for the manufacturer, the optimal strategy does not depend on the retailer's part because he is the leader. Okay, so let's discuss the equilibrium outcome. The manufacturer will offer the wholesale price 1/2, and that's going to make the retail price 3/4. And this verifies our intuition. For the retailer, the retail price will become larger than the wholesale price. Here, economists they use the term double marginalization to describe this phenomenon. When we have two players in a supply chain or 2 layers in a supply chain, at each layer, the player must add something into the procurement cost because the player wants to make some money, so there must be a positive sales margin. So when we have 1 layer, the price will be increased 1 time. Or if we have 2 layers, the price will be increased 2 times, and that's going to make the price higher than that price when we have only 1 layer. Okay, so think about this. What we just said is that there is a manufacturer, there is a retailer, and then retail price. When we have 1 layer, the price will be marked up once, and when we have another layer, the price will be marked up twice. Compare that with something that with only 1 layer. We can say that, if there is only 1 layer, the equilibrium price will become smaller. That's also something that we're going to show you. But please know that this is the typical argument made by those I don't know how to say it, direct sales people. Okay, 直销啊. Oh, they always tell you that our products are cheaper because we cut down some layers and use a more efficient channel to reach you. And I suggest do not believe in them because their products are just useless and not very cheap. Okay, my personal opinion. Anyway, you can say that if we are really talking about an usual supply chain, then because there are two layers, both of them want to get some positive margin. So this is called double marginalization in a supply chain or in a distribution channel. Anyway, let's continue. So now we have the retail price. The sales volume or the sales quantity or the demand will be 1 over 4 because it's 1 minus R star. And then the retailer will earn 1 over 16. Manufacturer will earn 1 over 8. Together, they will earn 3 over 16. That's the complete description of our equilibrium outcome. Naturally, we want to ask, is that outcome satisfactory or is that outcome good? And that requires us to discuss about integration or cooperation. Let's consider the pricing problem in a cooperative supply chain. Suppose the two firms cooperate and together discuss what to do, what will be the prices. Then we want to ask, can they do better when the supply chain is decentralized? Okay, can they do better by doing integration? So probably one thing we can do is to really make them union and solve a single player problem. But let's think about this. Suppose somehow someone propose the manufacturer to charge zero wholesale price. Okay, somehow we know it's very weird because the manufacturer should not accept it. But let's simply analyze this option. In this case, the retailer's best response will be 1/2, and then the sales volume will be 1/2, and then the total profit is 1/4. In this case, this is the retailer's profit. The manufacturer's profit is 0, so together they can get 1/4 as the aggregate profit. And you can see that this is higher than 3 over 16. So that means suppose the two players sit down and make their decisions. So there is a host manufacturer and there is a retailer. They together decide what's the wholesale price and the retail price. Okay, there are two variables and they have all kinds of options. We only analyze a very simple option. Okay, W is 0 and R is 1/2. And then we can say this is better than the decentralized outcome. Then the answer is clear. This is just one option, and then it's better than the decentralized outcome. So that means if we do integration, there are all kinds of options. At least we can do this, and that's better than the equilibrium outcome. Okay, so integration indeed can benefit the two firms altogether because with integration, we are able to make a better decision to maximize the integrated profit. So in this case, what's more interesting is about consumers. We can show you that consumers also benefit from integration. Think about this proposal again. This is the retail price, it's 1/2. In the previous case, when we have decentralization, the retail price was 3 over 4. So now, under integration, price becomes lower. And then more consumers can buy this product. More people buy this product at a cheaper price. That benefits the consumers. Okay? So in this case, integration can benefit the firms, also benefit the consumers. Okay, seems to be wonderful. That there is one issue. For this particular proposal, the manufacturer earns nothing. So when someone proposes this, of course the manufacturer does not agree, right? The manufacturer will say, I'm earning nothing, I'm earning less than in the decentralized case. What's the point for me to cooperate with the retailer, right? So if we really want to make this proposal accepted by the manufacturer, we need to somehow give the manufacturer some incentives for doing that. So that comes into the incentive issue. Okay, in a decentralized system, we cannot control everyone's behavior. Okay, we cannot decide what to do by the manufacturer, what to do by the retailer. We cannot determine their actions. What we really need to do is to design an incentive system to give them incentives to induce their behaviors. Okay, just like here. If I am a manufacturer, I think about this situation and I say, I want to earn more money, and that somehow requires the sales quantity to be larger. Then one thing I can do to induce the retailer to decrease the retail price is to lower my wholesale price. Okay, if I lower my wholesale price, I can induce the retailer to lower the retail price to increase the sales quantity. That's something I can do as a manufacturer. I cannot control the retailer's behavior. I can only induce his or her behavior. Okay? It's just that if I do so, it's not very good because the optimal strategy I should do is just one half. So anyway, here, just remember 2 points. First, decentralization hurts everyone. And to really achieve an integrated outcome, we need to have some incentives provided to the players. And that will be the topic 1 week from now. Okay, take a break. Thank you.